All right. So today we want to talk about two things kind of relevant to each other and relevant to things that we discuss. Do we have any questions before we get started about the last lecture? How many of you started looking at the project? I see some. Did you manage to compile? Did you do make clean? It doesn't work? That's weird. Did you try to remove all the like files in the binary?
Yeah,
Even that? Did you try to just do manually, like just GCC compile? Yeah.
I think it works on like native Linux, so I tested it on a Red Hat operating system, and that worked. But when you try like WSL, like returns like there's like multiple definitions of like better variable or something like
I see. I tested on my Mac, like my native Mac, and it works fine.
that.
Yeah, but yeah, it doesn't use any fancy. You can just use like a regular, like simple GCC your own commands. But let me know if you have more issues. Okay. So few people started looking at it. It's I would say it requires a little bit more of kind of learning compared to the other two computer assignments, because you need to kind of educate yourself about the timings and the power and kind of the basic operation of a DRAM, specifically in the context of that simulator. So spend a little bit of time to understand that before kind of jumping into uh to the design part of it. So just kind of factor that in when you want to start. So I mean, if it's Tuesday, probably if you start on Monday of the day before, it might be a little bit too late. Anyway, so let's talk about two important things that are kind of relevant to the stories that we said so far. So if you remember when we were talking about side channels and microarchitectural side channels, we said that we already have systems in place in our system to make it secure. And then the main things that we said that these are the main kind of ways to protect our system. The first one was principle of least privilege, which essentially we don't give access to certain things and data and memory if we don't have to, right? So you have to kind of minimize it as much as you can. And usually we have like root user and root. But in more modern systems, there are multiple layers. There's like a machine layer and the root level and so on and so forth. The second thing, which is kind of the most important aspects of any of these computer systems in order to achieve security, is the isolation principle, which essentially every process has its own kind of user space, its own memory space, and cannot read or write other parts of the memory if they don't belong to that particular process. And then we use a bunch of like, a combination of various hardware and software, solutions to make sure that this indeed works. And lastly, we have this thing called Trusted Computing Base, or TCB, which essentially, like all of these ideas that we say, is based on this part that we do trust. If that part we don't trust, then essentially all of these things that we say no longer works, because there's no trust. There's no one that can enforce that kind of principle. So everything is kind of up in the air. And then when we're talking about microarchitectural side channels, specifically things like CAD side channels and transient execution attacks, including Spectre and Meltdown, and the other variants that you've probably seen in the paper presentations, we saw that this isolation assumption kind of breaks, unfortunately. And hopefully, if you have watched the videos for the presentations, you also saw some of the defense mechanisms for this, how one can re-isolate the system, how can one, protect the systems against side channels, and so on and so forth. If you haven't watched those videos, you should definitely watch it. It's part of your class. So, spend some time watching the videos, kind of learn about those papers. It's very important. And then if you remember, we talked about various different side-by-side channels, kind of digital and physical, and specifically focused on digital side channels. But so far, the things that we've discussed is mainly around this kind of basic assumption that At best, you can read information that you're not supposed to read, okay? But you cannot introduce additional errors to the system. You cannot write to the arbitrary part of the memory and so on. So side channels at best was this capability given to the attacker that they can essentially read whatever they want. They can read arbitrary part of memory if they can launch a very sophisticated attack. But the bigger question is that can now adversary be, for example, from a more passive role to a more active role, which essentially they can arbitrarily write various parts of the memory. And this is the story of memory safety, which one way or another, probably you've seen it in many different courses, including courses I've taught in the past. And essentially the idea here is that the adversary can write things to the memory. And this write could be either temporary writes, for example, changing registers. When I say memory, I mean memory and registers. So it can kind of change the registers to cause some problems, or it can do a more permanent damage by writing to the kind of like an external memory or non-volatile memory and so on and so forth. And you have already kind of seen an example of this rowhammer last time, which essentially by kind of like accessing a particular row, the adversary managed to flip bits on the other rows, right? So, oops, sorry. Okay. So if you remember the rowhammer idea that I showed you last time is that if I have this oh, is it not connected? Give me a sec. Okay, sorry about that. So if you remember, like the memory, like this rows, and then somebody, if you keep writing in this row, you might be able to kind of flip bits in this row or this row, and this is a very important kind of capability by the adversary, because not only we have shown that someone can read this arbitrary values using these different side channels, but now we're saying that by just running my code here, essentially I can kind of like impact the rest of the system, right? And that's a big problem because, again, the isolation assumptions that we have could be broken by this kind of additional capabilities. So why we can do this? At the memory level, the main issue is someone can write using pointers. So usually the pointers could be exploited in the temporal time, or it could be exploited in the spatial time. So if someone, for example, if you free a pointer and later on you reuse it, so this is use after free kind of situation, then essentially you can write arbitrary things into that point in the memory that used to be something else. Additionally, you can kind of do out of bound writes, which assuming that, for example, your pointer is supposed to be 40 characters or 40 blocks in the memory. Now, if you somehow don't check the bounds and be able to write outside the bands, then you can actually do write into other parts of the memory. So generally, there's kind of two categories: the temporal category and the spatial category that one can write to the memory. And then there's tons of these kind of ways that one can do this memory safety attacks. We're not going to talk about the ways that one can do this, but what we want to show you is more of like the general view of this, and then in the paper readings we're going to see how one can kind of protect the systems against this. Okay, so if you think about these two capabilities, the temporal and spatial, And then see what could happen based on this. There's this actually like gigantic diagram that you have to pay attention to. And memory safety is one of the oldest problems in security and system security. That's why there are kind of tons of different attacks that is happening in the systems. Long story short, again, you probably have seen all of these, but let's actually review it together. A long story short, the attacker can essentially be able to do 4 different things, okay? The attacker can, the main one that probably you've seen it a lot is what we call the control flow hijacking, right? As a result of writing something to either the registers or the memory or combination of both, the attacker can basically run arbitrary codes, either the code that's injected from outside or reuse the codes that's been part of the memory itself and attack the system. Let me close the door. The second and also very important group of attacks is data-only attacks that the adversary doesn't necessarily change the execution, the sequence of instructions, but change some data during that process. So for example, consider a system that based on particular flag or inputs make a decision. And then if you kind of corrupt this flag, then that decision is different. So you don't really change the sequence of instructions. You still run the same application as you're supposed to, but the data, the input data or the output data is not the one that you were expecting. So these are the 2 big categories of attacks. In addition to those, there's also another 2 categories that is also very important. There's one that is you can leak information by using this. So essentially, if I can arbitrarily write things, then maybe I can also do some form of kind of data dependent, activities, and as a result, may be able to flush other things out of the system. Or I can just corrupt the system and then do some form of a denial of service attacks. Okay. Together, these are what we call memory safety problems. And essentially, this is very, very powerful, group of attacks an adversary can have. They can do multiple of them together or can do one by one. Okay. So let's actually see how these things happen. So remember, I told you that the attacker could do either out of bound. So this is what we usually call spatial, or do dangling or making using a pointer that is supposed to be not used anymore, and this is a temporal problem. Using either of those 2 or both of them, then the attacker gets 2 capabilities. The attacker can either be able to use the pointer itself to write or undo writes, in other words, free, or you can use the pointer to read arbitrary values. So either of these 2 is possible when you have now control over reading arbitrary values. Okay. So using this 2, now the adversary has essentially kind of 5 different capabilities that they can use. Okay. The adversary could modify the data pointer, the code pointer, the data pointer itself. Okay. So if I can kind of change a pointer, I can further change the pointer. And as a result, when I further change the pointer, I can do additional things. So essentially, this kind of creates a loop for the adversary that, once I can do one thing, like once I start finding a hole, I can make this hole kind of bigger, right? So it can give me more and more opportunities. And then I can write another pointer. Eventually, once I have that capability, I can do one of these 4 more kind of potent things. I can modify the code. Okay, so since I have control over kind of arbitrary part of the memory, I can just change the code as I wish. Okay, I can change the pointer to the code. So for example, if there is a return address or there is a jump or there is an indirect branch, I can change that pointer. And changing that pointer then gives me to control the control flow of the system, because now I can jump to the various different parts of the program. I don't necessarily need to write things, but I can jump to these other parts. So this is more of the code part. I can also then focus on data. I can change a particular data as I wish. Again, if I have control over writing arbitrary parts of the system. And this data could be either the data variable or it could be the output data variable, like the output of the system. I can do that too. Okay. And then again, the story here, you've probably seen this one in the middle more. So once I modify a code pointer, then I point it to a particular address. Okay, this address could be the address of either a code that I injected myself. This is typically referred to as shell code, which is usually opens a shell, or it could be any other system calls or any other activities that you wish. Or I can just run into some part of the same code system, and this is typically what we call a return-oriented programming, or ROP, which probably again you have seen, and in my past course we kind of extensively talked about, which essentially you don't want to necessarily inject something to the memory, but there are enough interesting things in the memory itself that you want to just reuse them. Okay, and then if you go further down, once you do either shellcode or the gadget, then you can either use it to do an indirect jump or call, and as a result, you can either execute the injected shellcode or execute the gadget and function. And in both cases, eventually you are doing what we call the control flow hijacking. You hijack the control flow, then whatever malicious activity the device wants to do can do that. The other route is you can just, instead of using an indirect call or jump, you can use the return instruction. And the same story, once I have the control over where to jump, I can either jump to execute a shellcode, or I can jump to execute a gadget. And then I can repeatedly do this, right? So once I have the control. So this is the story of the control flow. If I don't want to kind of jump to different parts of the program, I can just say, okay, I want to just modify the code itself. And when I modify the code itself, then I can and do some specific attack, right? So I can actually do whatever I want to do. Usually modifying the code has some implications, because most of these systems don't let you to read and write from the same part of the memory. So usually, code is either writable or executable. As a result, this is typically not an easy attack to kind of pull off in most systems. But assuming that you can, then essentially you can corrupt the system and do whatever you want again with. Okay. And then in the kind of like this right half of this figure, one can actually modify a data variable to the attacker specified variable, use that corrupted data variable in order to do some form of data only attacks. Same thing could happen for the output data, and then you just corrupt a particular output data, and then that output data would be interpreted by the adversary in order to leak some information. So for example, let's say based on, think about an encryption algorithm that based on the key and the input, I'll see an output. And then if the adversary can control this input and output, they can maybe create some form of a mathematical formula to kind of extract the key, right? So this is kind of something to, here, I don't want to corrupt anything. I just want to know what is the key, okay? So this is kind of the entire landscape of memory safety systems. You can either corrupt the data or the code. As a result, you can do various different things in the system. There are tons and tons of papers on each one of these. And again, both me and other courses we probably take in, we went to the details of each one. We don't want to do this now. We just want to give you an overview of these type of attacks. Any questions so far? Yeah.
Do most of these issues just go away if you use a memory safe language?
So it's a good question. So essentially, if you eliminate this, the top of the tree, then everything else kind of is eliminated, right? So, but memory safety elimination is not easy. First of all, yes, for future systems you might, but for old systems you can't, right? So you either have to Like you rewrite all the old code that you have using the new language. But then there's also always bugs. So it's not just memory safety, it's also sometimes the design bugs that might be there. But yes, if I don't have these yellows, I'm not gonna have any of these blues. So yes, that's kind of solves the problem. Any other questions? This is another table that's kind of showing the exact same thing. So essentially, you can think about the problem as the integrity problem. Okay. So the memory safety is that one way or another, you corrupt the memory, either using spatial or local or temporal. Then you can either change the code, you can change the pointer to the code, you can change data, or you can change the pointer to the data. In all four cases, you're changing the integrity of the system. You can also, after changing the integrity of the pointer, if you're using the pointer, then essentially you are changing the location of that pointer, right? And as a result, then you can do either code corruption or do data-only attacks. If you use that location in order to do something else, then you're essentially either going to have, control flow types attacks, or you can have a more sophisticated data-only attack. So you change a pointer, you use that pointer in some other code, and as a result of that, you have something either leaking or changing the data and so on and so forth. So it kind of like he also very nicely kind of show you the kind of landscape of these memory safety attacks. Okay. So how do you defend? The defense, so there is also a range of solutions for defense. So of course, number one is finding and fixing the bug, right? So either use memory safety languages or add proper checks so that you don't have these kind of temporal spatial bugs. There are a whole suite of software solutions for this. These include, like, for example, compiler level solutions to do these checks using language safe, memory safe languages to not have even this kind of like problems and so on and so forth. At the hardware level, there are also tons of solutions that we're going to talk about in the next few slides. There are two large class of solutions when it comes to memory safety for hardware, and this would be the things that you will learn in your paper presentations. We're going to see next week. So the main thing that people usually do is including some metadata and perform security checks at runtime. So essentially, when it comes to hardware, the main thing is that you can do this as the system, execute. So the nice thing about having a hardware solution is that you don't necessarily need to eliminate the source of these attacks, but as they're trying to kind of like, doing some form of corruption, you kind of catch them and then you prevent it from happening. Okay. So what do? We usually, for example, do bound checking. So for example, knowing that this particular pointer is supposed to kind of have this range and that range, if I see an access to a memory that is beyond this range, I can detect it and prevent it from happening, right? Another thing is that you can do the same thing for temporal safety, right? So if I deallocate the memory, I can have this method to detect that something is being kind of deallocated, no longer needs to be used. So I can actually detect that as well. Okay. So going back here, essentially looking at all of these things here, the attacker can essentially the hardware can essentially detect any instances of these things that is happening. So I'm still dealing with my legacy code that has these bugs, but at least I detect the existence of these bugs and do something about it. Okay. The second idea that we usually so it's kind of like using this kind of metadata and then do security checks. There's kind of two groups of ideas that we follow. The first one is control flow integrity, or CFI. The idea is that if you are really worried about the code, what we need to do is making sure that all the transitions are valid, right? So if I want to make sure that the adversary cannot change the direction of my system, my code, The code cannot jump into arbitrary locations. All I really need to do is kind of knowing what is valid and what is not valid. And then during the execution, I can, kind of adjust that. So again, this is some metadata that we are adding to the system. And then during the runtime, we are kind of enforcing that metadata. So there are tons of questions here. The main two ones that you have to kind of consider when you're applying any sort of CFI is, how do I know that these are valid transitions, right? So valid transitions is the kind of like the key here for in order to detect whether something is happening or not happening. So I need to know all the valid transitions, and this is the story of, oh, you need to design your CFG, you need to have good coverage, and then a whole bunch of things such as fuzzing and symbolic execution and all those things essentially goes into this category number one. The second thing is that, okay, now I know what are the possibilities of valid and invalid. How should I enforce this? How should I check this? How should I even implement this in hardware? How do I like remember all those different valid checks and all those things? So things that are purely implementation. And as a hardware designer, you guys should think about these things mainly, right? So like, for example, if I have a list of all valid transitions, how do I even check which one is which? What sort of data structure should I use? How to enforce this in hardware, and so on and so forth. So there are these interesting questions that one need to answer. And when you're reading these papers, you will see that kind of like these are the questions that keep popping up, and different people have different solutions for them. So I encourage you to kind of take a look at those and pay attention to the presentation next week so that to see this differences. An example of this is actually the control flow integrity is actually first introduced in 2005. And the kind of idea is that, you have a, code function like this, that you have a bunch of different functions like LT sort and sort two, then you essentially going to have these kind of like weird, distribution of these different instructions, that from this you can jump to here or here, from here you can jump to here, from here you can jump to here, and so on and so forth. So what I need to do is kind of like creating this CFG, control flow graph, to know what is allowed and what is not allowed. Once I have this map about my system, then during the runtime, whenever I have a jump, then I'm kind of like, query this kind of control flow graph and see, have I seen this before during the kind of like, profiling phase of my application or not. This is actually what's been implemented in real systems. So the main one is this technology called control flow enhancement technology, or Intel CET. So Intel CET has two main components in order to ensure that control flow integrity is preserved. It has this shadow stack system, SS, which essentially the idea of the shadow stack is that, if you remember how control flow integrity works, is that essentially you're kind of, you using the code pointer to override things. And as I told you, you either override return addresses, which essentially you override the return. And if you override the return, and if you remember the picture here, once I kind of like code pointer override the return, then I can either do, like, I can do arbitrary things, right? So what I can do is that eliminating the chance of overwriting return. How do I do that? Since the return is the function that's stored in the stack, I have this additional stack called shadow stack that is not visible to the user, but it's only maintained by hardware, right? So wherever I have that, I check this with shadow stack, and then if these two matches, then I'm good to go. Okay. But this only fixes the problem of returns. There's tons of other things that we need to worry about, and these are mainly the indirect branches. So for example, if you have something like this, an indirect branch that essentially jumps into the content of the particular register. For example, in this case, you have an instruction like this that jumps to the content of RDX. If somebody change RDX, then essentially they can jump to arbitrary part of the system, right? So what can we do in order to kind of prevent this? The idea that CET is using is using this additional instruction called end branch. And end branch is essentially just marking what are the possible places that a jump can jump into. In other words, if there is an indirect branch, interprocessor does not allow you to jump into arbitrary locations in the code. It can only allows you to jump into this end branch instructions. Okay, this way I cannot, for example, create gadgets in the system. I cannot jump into the middle of a particular instruction. I can only jump at locations that are kind of marked with this end branches. Okay, and this is for all sort of like jump oriented or return oriented programming like job and cope and ROP. These are all kind of eliminating all of those kind of gadget based attacks. To give you a little bit more kind of like details about this. If you, by the way, if you're interested, definitely search for CET. This is actually what is being used in many of these Intel processors. So again, the idea of shadow stacking is that you have maintained another part of the memory just for the shadow stacks. What happened is that, after the return, what we will check is we always check this whether this kind of like address that is these two are jumping to are the same. On the return, we're gonna pop it from both stack, and then we're gonna see if these two values are the same. If they are the same, we execute that. If they're not the same, then we're gonna issue an exception, and then the processor will take over and then do that. Interesting thing is that usually for different virtual machine or OS, there is a different shadow stacking. So we want to have process or isolation capabilities for different processes. And then on a call, essentially all we need to do is that we need to push the return address both on the regular stack and on the shadow stack. And then essentially when you have the shadow stack, there's no parameter passing on the shadow stack. That's the major difference between the shadow stack and the regular stack, right? And then the end branch for indirect branches, essentially end branch, by the way, is just a no ops. It doesn't do anything in regular systems. All it does is that essentially when you have a jump, the jump is only it can only jump into where the end branch is. If it jumps to somewhere in the middle, then again that will create an exception, and the exception will be handled by the processor. Okay? Questions? All right. So that's the like an example of a CFI, which Intel kind of handle it this way. There are tons of other works that kind of like handle it as well. Yeah.
What if it's jumping to like something stored in the register that's known at runtime?
Jumps into the something stored in the register.
Yeah, for the second slide at the bottom. Because it says it needs to add it by the compiler, but what if it doesn't know before? Like it's at runtime.
Oh, you don't know where to jump?
Yeah, like it's a result of something else.
So usually you jump, so you have to jump in, so it kind of limits you to where to jump to. But the limitation is usually you jump to the beginning of a particular function or beginning of a test case or something. You can have end branches on all those test cases if you want to. This is kind of like, you're never gonna like go to like to next line or like skip a few lines. There's always like particular spaces that you can jump to because these are usually function pointers, right? So at least these are the functions that you can put the end branch in all of them, but you cannot allow to jump in the middle. So this is mostly to prevent ROP-based attacks that you can find arbitrary gadgets in your code and then you can just keep running. And this is essentially saying that, oh, okay, I can only jump at the beginning of functions. All functions, doesn't matter. You can even reduce it, or you can be pessimistic and say, okay, all functions, okay. But this eliminates that kind of ROP-based kind of gadgets.
Where is the shadow stack implemented in hardware? Like, is it a sort of cache or?
So usually you either can have it as kind of an offset to the memory, okay? Or you can have it as a completely separate structure. Typically, the best way to do it is having it as an offset to the original stack. So wherever you store your stack, some offset to that would be where your shadow stack is. On all of these things are part of the memory, whether you cache it or not, depends. So typically, in order to understand what you cache or what you don't cache, so everything is in your main memory. Then you have these pages, right? So some of these pages will be cacheable, some of these pages won't be cacheable at all. Okay. Typically, we cache this. If you cache this, then we cache the entire page. Okay. And then same story happens for both code and data. So there's no really difference between those two. So if your stack happens to be some page, I mean, your stack ends up being multiple pages, and those pages are treated equally to any other pages. Typically, your stack is something that's going to be cached because it's going to be used a lot, but it may not be cached as well. But at the end of the day, they are just addresses stored in the memory. If you need them, you will cache them. If you don't need them, you won't cache them.
So I was just asking because like, let's say it's in the main memory and you're doing the like offset thing. Does the processor also need to like bring in the shadow stack to do the comparison?
Yeah, so shadow stack is just another address in the memory, right? So if I want to bring that in, I have to go first search my cache. If it's in my cache, then it's a hit. If it's not in the cache, it goes to the main memory. I have to wait. So this is a performance issue that might come with it, right? So for example, the return address, I need to wait to see whether the return address is there or not. And that's why generally, for example, you need branch predictors because of all these problems, right? But you also remember you had BTBs and you have all those other tricks. You have RASP, which was return a stack buffer, which for all the return instructions, you remember the address and kind of predict that. So in order to boost your performance, you do all those branch prediction tricks. But eventually, at the end of the day, your data is stored somewhere in the memory and you have to fetch it. Other questions? All right. So that's it with the CFI. The second kind of like big ideas for fixing the problem of memory safety is memory tagging. The idea of memory tagging is that essentially every pointer can be tagged with some specific tag. And the idea is that only, if I want to update any pointer, I have to update it with the tag itself. This will prevent any sort of illegal writes to the pointer, because if someone tries to kind of write a bunch of things and the pointer, they cannot update the tag, and the results, the tag and the data won't match. The next time we check the tag and the data, they will fail, and that's the way we're going to detect this. And then you can essentially expand this memory tagging idea not just to the pointer, but actually to every content in your memory. You can tag your code, you can tag your data, and you can tag your pointers, right? So essentially what I would do is that whatever I have, I also have a tag associated with it. And then if somebody wants to write to these, they have to write to the tags themselves as well. The famous example of this is this ARM pack, pointer authentication code. So essentially, if you have a pointer, a regular pointer, okay, and this is, by the way, what is implemented in all these Apple processors these days. So this is kind of like very interesting solutions for pointer authentication. So if I have a regular pointer, what I would do is that I take the pointer, I hash it, and then I will get what we call the pack, the pointer authentication code. And store the pack with the pointer itself. Okay, so for example, consider this as a 64-bit value. The idea is that usually this 64-bit values are not fully used. So typically we have 48 bits for virtual addresses, which means that around kind of like 16 bits or so is empty. I can use it for whatever I want. Typically they're all zeros. Okay. 16 or 17 bits. So the idea is that I can have 16 or 17 bits to store my my pointers, my tags into the system. Okay, so I take the pointer, I hash it into 17 bits using some form of MAC authentication algorithms. This would be the tags for this 47 bits pointers. Okay. Now, next time I want to use the pointer, what I would do is that I first kind of like take the pointer, hash it the same way I hashed here, and compare it with the tag that I stored in the pointer. If these two matches, then it means that I can use this pointer. Okay. If you're curious about the equivalent of this in R, so we have this pack IA, which essentially say that, for example, this stack pointer needs to be tagged. And then when I want to use it, I again use this, authentication IA in order to see that whether the stack pointer is indeed authenticated or not. Okay. So the idea is that if someone writes anything to the pointer, like the stack pointer or any other pointer, with using this kind of tricks, I first kind of say that, okay, this is the correct value that I should remember. If during this process, someone writes to this pointer, when I authenticate it, I'll see it. Okay. And now the idea is that if these two doesn't match, then what I can do is essentially kind of like run an exception, or at least, scrap this data and redo it, or things like that. Okay. And then this is purely hardware because it has to be run in the background, right? You have to be very fast. Of course, this will add a little bit of runtime overhead to your system, but we are talking about kind of authenticating and checking only very few times during the execution. So the runtime wouldn't be that. Yeah.
Would it susceptible to transient execution attacks?
It would be transient execution, susceptible to transient execution attack. Yes. Do you have an idea how?
Yeah. Spectre and meltdown, like they will do it out of order.
Uh-huh.
And whatever is after it can be executed in and could be present in the caches, and by the time it realizes that it was not supposed to do it.
Exactly.
It
Yeah.
It had already did it.
Yes. Yes. But it won't attack the tag itself, but it can be used to do to attack transient execution. Correct. But one good thing about these is that they are very fast. So it's not like as bad as, let's say, accessing memory, which is kind of hundreds of cycles. This is like 1 or 2 cycles. But actually, a very neat attack to this is one of the papers. I don't know if anybody is presenting it or not. It's called Pac-Man. And the idea of Pac-Man is this, that what I can do is, let's say I want to find this 17 bits, okay? The only way I can do this is just doing brute forcing, right? I can just search. But since it's 17 bits, it's not that bad. Okay. I can, if I run it multiple times, I can probably find it after a few runs. Okay. But the problem with these is that they don't let you do brute force because of this. So if you run 2-3 times and if it fails, it will cause an exception and then it's gone. Okay, so at best you can do 1 try or multiple tries at best. So what you can do to kind of like being able to run this brute force is using similar attacks to meltdown. If you remember, meltdown was I can create an exception, but if the exception happens in a speculative window, even if it throws an exception, it will be discarded, right? So if I put this kind of my kind of brute force attacks into a meltdown kind of window, so I put a branch here and do this kind of meltdown here, then it won't be captured. I can just keep running and running, and at some point I will hit the code, and that's when we no longer are going to see the exception. So then I can actually continue, right? So there's actually very interesting observation that these kind of like checking are all vulnerable to this meltdown-like attacks that you can capture the exception and discard it if it's in the speculation window. So you actually have to completely change the way that we kind of detect these kind of attacks, which is very interesting. But yeah, good observation. Any other questions? Cool. So there are a bunch of questions, for example, where to store the tag, how to move them, how much is the slowdown, what sort of hashing mechanism or macking mechanism should we use, what should we do if they don't match, does this always work? There are tons of these questions that, again, when it comes to hardware implementation, hardware designer needs to think about. And remember, all these things, security is always important, but as I told you many, many times in this course, performance is the king. So performance is the one that you shouldn't be able to sacrifice for this. So if I have this pointer authentication that says that, you know what, I'm gonna, eliminate all of your memory safety problems, but the cost of this is 20% slowdown in performance, nobody gonna buy that. Okay, so you have to be not only fixing the security problems, but also do it in very, very minimal way, such that the performance is not significantly hit. Okay, so that's kind of like the challenges that you will see in this kind of memory authentication, memory tagging. But memory tagging is getting more and more traction these days. It's very interesting because it can essentially kind of expand it into many, many other part of the system. For those of you who are interested, take a look at this thing called Cherry, the capability-based, memory tagging. This is actually allows you to different part of your memory have different capabilities, and this way you can actually add tags, remove tags, pass tags, have all this kind of pointers to them as well. So this is actually a very big project that ARM is heavily invested on. So most of their systems going to be some form of Cherry enabled in future. All right, so let's have a quick break. We're going to come back and talk about T's as well. All right, so the last thing I want to talk about today is trusted execution environments. And again, I want to mostly talk about T's from implementation perspective. Some of you may have heard about T's in the past and know how it works. For those of you who don't know what is a T, essentially think about T's as kind of taking isolation to the next level, right? So if this is kind of my regular system, right? What I can do is I can have this additional hardware area called the trusted execution environment that it has kind of its own mini operating system. It has its own mini like drivers and kind of firmwares. And then it has its own trusted applications. The good thing about this is that you can physically, or at least at the software level, create more isolation. And this is kind of in response to all these problems that we have with memory safety and or side channels, that one can actually kind of try to divide this from each other. That, of course, comes with a huge overhead in terms of hardware. But if I can at least have kind of like a truly trusted unit, then I can do some interesting stuff with it, right? So that's kind of like the very basic idea of a trusted execution environment. There are many ways of implementing this. There are many kind of assumptions and considerations for doing this, but the main motivation behind it is that I want to have kind of a really, really isolated, truly isolated environment in a somewhat kind of shared environment that we had in a regular system. So why do we need more isolations? Because of all these things that we talked about in this course. Because of large code, they have many software safety, memory safety bugs. It's really hard to remove them. There are tons of different side channels because of this sharing different applications together. There are many different vendors and designers that we don't trust. So maybe I can build my trusted execution by just one vendor and let others kind of fight over the non-trusted execution. And there are tons of sharing happening, again, on the non-trusted part. So because of all of these things, I need more isolation. So since I'm moving toward more sharing, more kind of bigger systems, scaled systems, maybe I can, now is the need to kind of have this secluded area for more security. The second thing is actually something that kind of came after the design of T. So T originally wasn't designed to provide this capability, but later people kind of say, oh, look, they actually can, extract more from your trusted execution environment. And that's the idea of what we call remote computing. So this picture kind of nicely shows this idea of remote computing. The remote computing comes from this kind of concern that if I want to run my code in some remote device, if I don't necessarily trust the remote device, but I still want to use the computational power, I can use kind of these tricks. So the idea here is that if this is the remote computer and I don't trust anything about this remote computer, what I can do is that I can create this smaller environment within this remote computer, quote unquote, the T. And within the T, I can create this, what we call an enclave or a container, such that I get some guarantees from the container itself that this is trusted. So what I can do is that essentially in the remote computer, I have tons of untrusted software, including the operating system, all the applications, so on and so forth. But then I create this container and I kind of push this private code and data to this container using cryptography. So I encrypt everything and then send this encrypted data inside the container. As long as I can, guarantee that data can be only encrypted within this container and outside this, the remote computer has no idea what's going on, then I have this isolated environment within this remote system, okay? And how do I trust this? I trust this by essentially trusting this infrastructure owner. Sorry, not this infrastructure owner, this software provider. Okay. Essentially, as long as I trust this third-party entity that kind of built this kind of container environment, then this kind of system will work. Okay. And again, there are tons of detail within, like, how do I create the container, and how do I send the request, and how do I receive the request, and all those things. Part of it we're going to discuss in the paper presentations next week. How do I build a T? How do I improve the performance of the T and all those things? But just keep in mind that this is kind of like a very basic idea of why you need remote computation. But again, remote computation is not the primary use of these, but these days is actually very popular use of these. Okay? So as I said, this is kind of like just repeating what I just said. The reason that we want remote computing is that we don't trust software, but we do trust our cryptography algorithms, and we do trust that the hardware kind of doing what it's supposed to do. So these two things we trust. Based on that, we build a remote computer. And then the reason that we don't trust is two things. One is either we don't trust that the operating system that kind of handling the remote computer is really secure. Why? Because of all these memory safety problems that one might have. Or we just don't trust the third party. So for example, consider a clinic that has some proprietary data and they want to use some form of a cloud environment. The cloud environment necessarily doesn't provide the trust level that the clinic wants. So they still want to use their setups, but they don't want to kind of like, upload the data. Now with all these OpenAI and ChatGPT and all these things, this actually kind of further exacerbated, because now you really want to use these machine learning models, but you don't necessarily trust them with your data. So this kind of remote computing actually is a very, very nice solution to that kind of problem. So that they can kind of upload their models in this trusted environment. You just upload your data within that container. You use that system without them really knowing what you did, without also them kind of compromising their system or providing any sort of additional information to your system. Okay. So if you think about the boundaries in a trusted environment, essentially when you go with like a regular system, this is kind of what we trust. We trust the hardware, we trust the hypervisor, we trust the operating system, and we trust the app. This is kind of our traditional way of thinking about trust in systems. But in trusted execution environments, and these are the three examples of three prominent companies, ARM, AMD, and Intel, the trust model is then different. For ARM, you usually just trust the enclave. Enclave is this self-containing environment that has this kind of its own quote-unquote operating system, and the code and data. And you essentially have just the enclave and the Intel SGX, the lower level hardware. And you only trust these two things. That's the only thing you trust. You don't trust the hypervisor, you don't trust the operating system, you don't trust the app, okay? The other apps. The ARM trust zone model is slightly different. The ARM trust zone model is kind of like saying that instead of every enclave having their own kind of thing, let's actually have one unified trusted operating system. And then we have a bunch of trusted app that runs on top of this trusted operating system. The difference here is that then you will have two types of operating system, the regular operating system and the trusted operating system. But then all of your apps just shares the same trusted operating system. And all of these things are handled by the hardware, the trust zone hardware. Then the SEV is kind of like the ultimate version of the trust zone, which says that, okay, let's actually have virtual machine level trusted. So all the way from the operating system to all the apps, but then I can have actually multiple of these VMs if I want to. So I have either the trusted VM or don't trusted VM, and SCV kind of provide you that capability of kind of like managing these VMs from each other. So it's very nicely kind of like model for server kind of grade computation and all, because it can kind of handle this at the VM line, VM level. Okay. And then if you again to kind of like just give you a little bit more, these are usually called what we call user level enclaves. So essentially, you can think about that. If I have what we call a user level enclave, which is what what SGX has, we have the application and we have the runtime together. So this creates one giant enclave, okay? And you can have many of these enclaves, right? So in SGX, for example, you can create a bunch of these enclaves, and they all work together. They all don't trust each other, and they don't trust the original system. So the original system has the apps, has the operating system of its own. This is just a traditional way of computing. Then I have my enclave, which has its app, and it has its runtime. And then I have a bunch of other enclaves that, again, they have their apps and they have their runtime. And then I have this layer of trusted software that kind of handles all of these things. And this way, I'm going to have my system. And then in DRAM, I'm going to have my OS. I'm going to have my trusted software. And I'm going to have my enclave. So essentially, the data is kind of nicely stored in these different options. The other option, this is more of ARM trust zone kind of option, is that you don't necessarily have the runtime, you just have the app, but then you have like more of a firmware or a layer of operating system here that kind of handles this. And of course, when you can have both, you can have also the combination. So you can have, for example, an enclave that has the runtime and an app. You can have another enclave that just is the app. And then you can also think about this as the peripherals now needs to be able to kind of further expand this. So for example, one enclave might access through some engines to some peripherals. Some other enclave can access to the other peripherals and so on and so forth. And again, in all the other sections of the system, you also need to kind of do this isolations for your system. So long story short, you can have kind of all three options. You can have just the enclave, you can have the enclave and runtime, and you can have just the app. And these are all the possible options for creating an enclave. Okay. Store again. So in your paper presentations, what you will see is kind of like, difference between them, the performance implications of this and all those things. In my previous courses also, we talked about this kind of difference between them a little bit more. So if you're interested, you can refer to those classes. For the rest of this, I want to actually talk a little bit about the macro architecture of a T and how, in a system with, the processor and the DRAM and the peripherals, where this T sits and what are the considerations that one needs to have. So from the computer architecture perspective, what are the important things that we need to do? And I'm going to focus on RISC-V based TEs because everything we did discuss so far was on RISC-V. So let's actually kind of focus on RISC-V. RISC-V has this open source project called Keystone. So Keystone is this RISC-V based trusted execution environment. And it's kind of compatible with Boom and Rocket and the rest of the SoC in RISC-V. If you're interested, take a look and search for Keystone. There are nice documentations and tutorials, similar way that there was for Boom. So if you think about an SoC of a RISC-V, we have what we call a tile. Okay, so a tile is a core with a bunch of other kind of memory units. So for example, we have a Rocket core or we can have a Boom core. In the class, we talked about Boom core, which was the out of order execution core of RISC-V. The equivalent of Rocket Boom is Rocket. Rocket is just a simpler processor. It's an in-order processor, older version of Boom. So Rocket is that simple core. Each core needs, if you remember last time I showed you that each core needs a cache, an L1I cache and L1D cache. From level 1, we usually have separate data and instruction cache. We also have the page table and page table walker. So each core needs to have a page table to translate the address from virtual to physical. Then from there, if you remember, we said that this is actually one core. And then cores are kind of connected to each other via some form of a bus. And then from there to the L level 2 cache. So we have this, what we, in RISC-V terminology, they call this a tile. Okay. And then we have what we call a tile bus, which is kind of connected this core to the rest of the cores. Okay. So the tile bus is actually where all these internal connections are. From the tile bus, then we are connected to what we call the system bus. So this is the unified system bus that all the other components in this system are connected. These are all part of one die. So this is one SoC usually. Then you can have multiple of these tiles. So nothing prevents you having a multi-core system. So you can have another Rocket core and have another Rocket core and so on and so forth. If you remember last time I showed you a quad core system. So you can think about that there are 4 of these next to each other. Okay. So on the system bus, then I have the big thing that I have is my L2 caches. Okay. And if you remember, L2 is not one unified area because it's too big. So you actually divide it into multiple smaller units that in RISC-V terminology, we usually call them L2 banks. So kind of like one big bank here and there. And then from the L2, then we have the bus to the memory, and that's where our memory controller was and all the stories that we talked about the DRAM and how do we access DRAM and all those things. So we have the memory bus and we have the tile links to AXI. So AXI, you can think about it as this protocol for communicating to the memory. There could be tons of other protocols that one can use. AXI is just one example of this. System bus is also connected to a bunch of other things. So not necessarily your system needs to be just cores and memory. You have peripherals, you have IOs, you have RF, you have all those other things. So your system bus usually then connected to what we call a control bus. And in this control bus, we have tons of different things. We have the ROM, we have the interrupts, we have the power, we have the JTAG, a debug unit, and all those other things, okay? So these are all part of what we call the control bus. And then system bus is also connected to the periphery bus. This is where all your peripherals, all your external connections, all these other PCIe cards, or if you have a GPU, or you have like an external disk and all those things, they are connected to this periphery bus. And periphery bus usually can handle multiple different technology and protocols. So you can have, for example, the TL2A, the tile link to AXI. You can have all these other devices that, let's say, you use PCIe or PCI or other kind of communication methods. And then this makes this system very scalable. So now you can have a bunch of things connected, but this essentially creates one SoC, in other words, one die in your system. then you can might have actually multiple of these dies connected to each other. Okay? Question so far?
When you say system bus, is that actually a bus or is it other types of interconnects?
Which one?
The middle system bus.
Oh, it's a well, what do you mean other interconnect?
Like crossbar or other networks.
Yeah, it could be crossbar. So usually it's literally a bus. Because like all of them needs to be connected. Sometimes, for example, if you want to really have a fast connection to the L2s, you have dedicated routes to all the L2s. But just for ease of like showing, you should use it as a bus. But yeah, internally you might have buffering, you might have direct connections and so on and so forth. Okay, so now if you look at your where your trusted execution environment might sit, typically we put our trusted execution environment within the tiles. Okay, so this is another example, this one with this what we call the ROCC accelerator. This is the coprocessor or on-chip accelerator, which in this case the accelerator is in fact the trusted execution environment. So again, we have, for example, this time we might have like either a rocket core or a boom core. Within the rocket core, you might have additional things such as floating point units and so on, which is not that much important. And as I told you have your L1 cache and L1 I and D cache. Then your accelerator is also connected to this tile. So it's what we usually call tightly coupled coprocessor, which means that the coprocessor and the core are tightly coupled to each other. So if I actually zoom this in, the tile will look like something like this, that this is my core, this is my quote unquote accelerator. When I say accelerator, I refer to any sort of logic that works as a coprocessor. So in this case, this is the T. So the T and the CPU usually have a literal wire-to-wire connection. So depending what you want, so for example, you can have a bunch of different in and outs. You can lots of control signals as well between them. You can have a bunch of different addresses. So you can actually define what goes in and goes out of each of these two units. And you tightly couple these together, okay? This is usually what we call a coprocessor, okay? That it sits next to your processor and then it's very, very tightly coupled so that they can talk to each other within cycles, okay? The other alternatives that you have is actually not having this here and going all the way to the periphery bus. So you can actually have a unit connected to here. And if you have a unit connected to here, the trade-off is that the cost of each of your tiles would be much less, okay? But the connection between this unit and your core is really, really high because it has to go through this bus and then this bus and then this bus and then eventually to the core. Versus in this tightly coupled scenario, you have a dedicated one-to-one channel, okay? So the big trade-off is but here the difference is that now you need to change the tile structure. In other words, now you need to add this additional things to your die versus here you can actually add it as either an external or you can even add or remove it later as another kind of component in the system. Okay, so keep that in mind that these are usually two connections that you have. Typically, we call this a loosely coupled system. Okay, so that one is tightly coupled. This one is what we call a loosely coupled. Okay, again, I can do some form of optimization. For example, have a dedicated connection from here to here, kind of improve the latency a little bit, but the latency from this scenario is significantly different than the latency from this scenario. So you might wonder, okay, which one should be used? That depends on the application. If there's something that you're anticipating that these two talking a lot and in runtime, then we need to have some form of a tightly coupled scenario. But if there's something that you offload and then you wait and you receive the data, then the loosely coupled scenario is much better option. Okay? Questions?
So something like for example, like a neural engine would
Mm-hmm.
be tightly coupled.
Yes and no. In some systems, no, it's not tightly coupled. In some systems are. For example, in iPhone, if you look at it, it's tightly coupled. It's part of like big SoC, and you have your CPUs, and then there's actually a very close connection between the CPUs and NPU. But in some other systems, it's not. It's just a separate unit to the system. Same story with GPU, for example. Typically, GPU is connected with PCIe, which is the express version is much faster, but it's not like one-to-one connection. Because think about this is that pins are expensive. So you cannot you might wonder, oh, why don't we connect everything directly to the CPU? Because pins, first of all, are limited, and second, are very expensive. So you cannot really just connect hundreds of pins to your CPU. There's literally no space. So that's why you want to kind of connect everything to a bus and then connect everything from the other side to the same bus. So continuing with Keystone kind of have this kind of format. Remember, I told you that different systems has different Ts has different kind of models. Keystone kind of follow this format of it has like the regular OS. Then for each app, it has its own runtime and it has its own enclave. In other words, kind of following the SGX route. And then it has this thing called security monitor or SM, which is kind of works at the machine layer and then controlling everything, including the OS and the runtime. Remember, I told you that we have different privilege levels. In RISC-V, we typically have 4 different levels. We have the user mode or U mode. We have the supervised mode or S mode. We have the machine mode or M mode, and then we have the hardware itself, which is like literally at the hardware level. So typically we have 3 different modes and the hardware. The SM stays at the lowest possible level, the highest possible privilege, which is the M mode. The operating system and the runtime stays at the S mode, and all the apps stays at the U mode. Okay. There are 4 things that Keystone does that's kind of like to improve the isolation. The main thing that Keystone does is actually doing cache partitioning. The reason for cache partitioning is Keystone wants to eliminate the cache side channel attacks. So if this is your regular system that is not secure, for example, you can have code for your security module and your regular applications and your enclaves and your untrusted applications like this. You can have a combination of all that. And of course, this will result in various different cache side channels attacks, if you remember, that if I have a trusted a secure application, a non-secure application can kind of like read data off of the cache. So cache partitioning algorithms essentially saying that what we should do is that kind of doing way partitioning, that for example, saying that enclaves only access to way 0 and way 1, and untrusted applications access to way 1, way 2, and way 3, for example, for a 4-way set associative cache. So essentially, you're kind of like literally partition the cache into parts. And then when you do that, then you also store them at separate location in DRAM. So this way, I kind of eliminates all the possibilities of cache side channels. Of course, this comes at extra performance overhead, as we discussed multiple times in the class. Another thing that you can do is that you can actually have some form of on-chip enclave that actually what it does is also kind of like doing separate cache partitioning. So essentially what it does is saying that, okay, I can have my internal caches that stores the SM and enclave and have this unsecured cache as part of the regular hardware that just is dedicated to untrusted apps. So in other words, I'm kind of like physically separating the caching mechanism completely so that I can actually achieve even more security. Last thing that Keystone does is adding encryption. So given that, the data between the cache and memory could be also snooped, and someone can, for example, do row hammer, or someone can like read data off of your main memory. The idea is that I can actually encrypt data when it's leaving the cache and going to my main memory, to my DRAM, okay? So what I can do to fix this issue is that I can encrypt the data once it leaves the cache. I can encrypt it using software mechanisms, but I can use it, I can also encrypt it using hardware mechanisms. So this is the memory encryption engine, or ME, which what it does is that whenever data leaves the cache, encrypts it and then put it into the DRAM. So this kind of two-level kind of cache partitioning plus encryption kind of protect the system from variety of different attacks to the memory system, including side channel attacks and kind of row hammer kind of like it. It doesn't solve this memory safety issue, but it solves some class of issues. Yeah.
Oh, are these like different options, or are those like everything that this T is doing? So are these like options?
So these are all implemented in Keystone, but Keystone is configurable, which means that you can actually pick and choose which of these features you want to activate it or not. So you can technically choose where you want these features be on or off for different applications.
I'm seeing a lot of trade-offs here. So for example, the cache partitioning and the on-chip enclave.
Mhm.
If you keep the SM in DRAM, then you're still susceptible to row hammer attack.
Yes.
The little white strip in the middle could like affect the two sides.
Yes.
But then if you move it into cache, then you sacrifice your cache performance, and then you're safer.
Good. You're a proper computer architect. There's no one kind of silver bullet solution, unfortunately, right? So this comes at a cost, either performance cost or storage cost or implementation cost. Yeah, these are all exist. What this gives you compared to like a normal system is that it gives you an option. So if you want to run something that security is much more important than performance, then you go with this. If something that's kind of performance is more important, then you go with the regular systems. This is kind of the entire idea of T is exactly this, that if I want more isolation in this kind of crazy system, this is what this is, right? So I'm not gonna fix the entire problem. I'm just giving you kind of a arbitrary, like temporary or kind of like minimal solution of a bigger problem that we couldn't really solve. Any other questions? All right, so there are some challenges, of course. I think we kind of had this discussion. The first question is that, is this really safe or not? Are we really fixing some problems? And surprisingly, there is still some side channels attached to the trusted execution environment itself. So for example, people have shown that if you don't really do this isolation properly, then there will be attacks. People have shown that, for example, yes, you've fixed this, but there's contention on the bus that someone can, for example, tap into and then find that. So there are attacks like that. There are people shown that, oh, if you actually change the voltage and frequency, you can kind of create some faults, and as a result, kind of can extract information. So T is also kind of now is kind of the focus of many of security researchers, because people say that, oh, okay, forget about the problems that we have in the CPU. T is the one that is not really susceptible to side channel attacks. So now everyone are focusing, showing that, oh, okay, let's essentially the same issues that you had in the regular processor, you're going to have the same issues in a T environment as well. Some of them are true, some of them are not. So that's one very big challenge for T's in general. Yeah.
On the last slide, when you're showing like some of them, I guess, pages or memory are in the enclaves. How is that possible without having encryption between the DRAM and the last layer cache?
Which one of these?
Like, for example, the first one.
This one?
Right.
This one is just a baseline system. It's no security at all.
Oh, okay.
So like read it this way. So here we have both partitioning and encryption.
Okay,
Okay,
I got it. now.
make sense?
Yeah.
Okay. So that's why, for example, here you see encrypted enclave, but there's no encrypted enclave here, right? So that's number one, that all of these things we do, we still don't fully fix the problem. The second is, how do we balance security and performance? True isolation, you reduce utilization. What about parallelism? What should we do with that? That's also like, very exciting area for research for many. And then the third question is, if I want to, for example, read data from IO or offload things to the GPU, then what should I do? So when it extends to the other components beyond the trusted execution environment and the CPU, how should I maintain the trust? Because T never works in their own isolation. It needs to talk to the IO, it needs to talk to the NPU, it needs to talk to the DRAM. So just staying in like a tiny isolated environment is good for some applications, but for the majority of applications, at some point you need to kind of branch out. And that was the original problem that CPU had. So CPU wasn't also as bad as today. It usually was a good, separate and isolated unit, but then we add all of these other things to it, and then it starts to blow up. And the same story is kind of happening to T. So now we need to kind of have a systematic approach that, starting from the T, how can we actually kind of spread the trust and having a systematic ways of maintaining the trust. So there are tons of interesting works of extending T's to GPUs, extending T's to IO, extending to the neural engine, and so on and so forth. So this is kind of the future of computer systems and computer architecture, would be things like that we're going to not have just one T, we're going to have a T that is spread across your entire system. Okay. So to kind of summarize, what I wanted to discuss today was systems are hardware systems are vulnerable to a large class of attacks. We talked about hardware concerns, including the transient execution attacks and side channel attacks before. We also talked about physical and fault attacks, including Rowhammer, also this week. But another large class of attacks is attacks that happens at the software layer. So this, by running the software, you're introducing new vulnerabilities. And in order to fix them, you need to either fix the software, which is a very hard problem, or you use some form of hardware method to at least, detect that bad thing is happening and immediately prevent it. And then we talked about kind of two big solutions, both of which kind of revolving around having some metadata and kind of checking that metadata. The first one was some form of control flow integrity checks that, for example, you have a shadow stack, or you have kind of like, a unit that kind of checks where you can jump to or where you cannot jump to. And then the second group was kind of tagging the data and memory and code and pointer and all those things. So that was kind of one category of solutions. The second category is that saying that, okay, we need to live with these vulnerabilities. Let's actually have kind of like a more isolated environment, which we call T's. And let's actually build this T correctly. And for example, let's do cache partitioning, let's do memory encryption, let's kind of prevent it from sharing and all those things. And hopefully this will save some of our problems. And in reality, it does, and it doesn't, depending on different cases. But what we really need to do is kind of expanding these T's to other units, and that's kind of what we're expecting to see in future. So next week, we're going to see a lot of papers about these two group of topics. So on Monday, we're going to see papers around software, memory safety, software solutions, hardware solutions, authentication, and so on and so forth. Actually, no, on Monday, we're going to see Rowhammer-based papers. On Wednesday, we're going to see this kind of software security. And then next week, we're going to see, T and T execution environments as well. All right. Any final questions? All right. Yeah, see the cats. All right, guys. Thanks.